Oh man, I'm never gonna make it to underwater basket weaving on time. Whatever am I supposed to do?
Well, Eddie, do we have a solution for you? Hi, I'm Nate Cito, part of the Atlas Project, and this is Albatross.
Hi, I'm Evan Steers, a mechanical engineering student. The Atlas team is one of the first researchers into the field of affordable, autonomous aerial transportation. When cars were first invented, it took decades for them to outnumber the current transportation on the road, horses. While today's world is advancing faster than ever before, it will still take years before this technology is widely available to people of all classes. When that day comes, we hope to have had a positive impact on the journey that takes us to the skies.
Hi, I'm Josh Gross, Mechanical Engineering. Our first goal of this project was to build a small-scale test aircraft named Hummingbird. It would be electronically similar to the large-scale aircraft, and we could test all of the flight capabilities of our flight controllers and electronics on this aircraft. Our second goal was to design, test, and build a large-scale multi-rotor named Albatross, which would have the capability of carrying a 220-pound person for short-distance flight. Albatross is in the final building stages, and we will start flight tests soon. From here, optimizations are being made to reduce the weight of Albatross and increase the aerodynamics, therefore increasing the flight time and range of our system.
Hi, I'm Cody Blocker, a mechanical engineering student here at SDSU. Last year's team designed the frame using 6061 T6 aluminum and an 1/8 inch thick. The frame was bonded together with the preferred method of MIG welding using 4043 series filler wire and argon shielding gas. The landing gear was redesigned using Fox Float 3 air chamber shocks. These shocks were chosen for their outstanding performance, as well as a built-in factor of safety of 3 for our purpose, and also rider comfort for when the drone lands. Lastly, the landing gear was designed, sort of like helicopter skids, to distribute the weight of the drone for an even landing on the ground.
The propulsion system is made up of 47-inch carbon fiber propellers with MAD component 43 kV motors. With an all-up thrust capability of 1,234 pounds between all 8 motors and propellers, we should have a 2-to-1 thrust-to-weight ratio on Albatross.
Hi, I'm Andrew Hanshaw, one of the electrical engineers. Each of our motors is connected to a set of 4 batteries for a total of 32 lithium polymer batteries. These batteries are connected in series for a total of 100.8 volts DC when fully charged. To connect our motors to these batteries, 8-gauge silicon wire is used, which is capable of 200 amps continuous load and even more in short bursts. To control the motors, an electronic speed controller is used, which is connected to the flight controller using this connector, which gives it a PWM signal, and each motor can be controlled independently.
Our battery mount was designed with passenger and battery safety in mind. Through some calculations and adding a factor of safety, our battery mount was required to stand up to 11 times gravity, or over 2,000 pounds of force. To secure the batteries, slide-resistant material was placed on the batteries and the battery mount, as well as a cage system over the top of the batteries to prevent vertical movement.
Rather than charging each of our 32 batteries individually, a system was designed to charge 4 batteries at a time. A commercial battery management system was purchased, along with a set of power supplies that are capable of providing over 110 volts DC. The power supplies are then connected through the BMS, which measures the voltage on each cell of the battery to ensure that no cell is over or undercharged.
Thanks, Atlas Group.